Hello, welcome to another series of simple bending. Here we will be dimensioning bent rods. But as an introduction, I wanted to show you the geometric characteristics, specifically the basics of these characteristics, which will be needed for dimensioning bent rods. And as I said, you won't learn complex geometric characteristics from this video. I will only show you the basics and show you how to read the table when it comes to geometric characteristics. I will briefly discuss this table now. In this table, we have basic figures for which moments of inertia have been derived. And we will mainly be interested in moments of inertia with respect to central axes. That is, with respect to axes located in the center of gravity of the figure. Additionally, in most tables, you will find moments of inertia with respect to axes, which are located at the beginning of the figure, but that will not be needed for us. We will focus on moments of inertia with respect to the center of gravity. Here are the moments of inertia with respect to the vertical axis, which is marked as yi here, and the horizontal axis marked as x. However, I would not get used to these notations, as they are often used interchangeably. Instead of x, it will be y, and instead of y, it will be z, simply with respect to the vertical and horizontal axes. And when bending, we will be interested in bending with respect to the horizontal axis, meaning here it will be moment x. And we have basic formulas, you need to know this. Here are the basic formulas with respect to axis x, axis y, and deviation moments. However, the deviation moment will not be needed, so I will not discuss it here. In some tasks, but we will not do such tasks, moments of inertia concerning the axes marked here in the drawing may be useful. Having a composite figure, such as a T-section, which is composed of two rectangles, we will have to use Steiner's theorem, knowing the moments of inertia concerning the center of gravity of the figure. If we divide this figure into simple figures, meaning the T-section is divided into two rectangles, we can first calculate where the center of gravity is, and then use Steiner's theorem to find the moment of inertia with respect to the center of gravity of this figure composed of two rectangles. Steiner's theorem allows us to calculate the moments of inertia of flat figures with respect to axes that are parallelly shifted relative to the central axes, that is, the axes passing through the center of gravity of the section. So this is the basic formula that we will use, which is the moment of inertia with respect to any axis parallel to the central axis. It is equal to the moment of inertia with respect to the central axis, meaning from this basic formula, plus the area of the figure we are calculating, and multiplied by the distance between these axes, that is, between any axis parallel to the central axis. This is the distance d raised to the power of 2. And on the next slide, we also have moments of inertia concerning a semicircle and a quarter circle, and concerning a square, but it's actually the same as with a rectangle, only here instead of bh to the power of 3, we just have a times a to the power of 3, that is, a to the power of 4 divided by 12. Now let's practice Steiner's theorem on a semicircle, because here you have already derived the moment of inertia with respect to the central axis. Or perhaps it is more elegant to calculate it, because we know the moment of inertia for a circle, so if we wanted to derive it from Steiner's theorem for a semicircle, then first we need to know where the central axis is, and that it is at a distance of 4r over 3 pi. This is the distance from this edge to the horizontal central axis. This distance is indeed 4r over 3 pi. And if we know the distance from the central axis, we know the area, well, obviously it's not a problem to calculate, and we know the moment of inertia with respect to the x-axis, which is marked here, then we can calculate the moment concerning the central axis. And the moment of inertia with respect to the x-axis here is half the moment of inertia of the circle. So using Steiner's theorem, we're accustomed to this form. We need to notice that we know with respect to any axis. We know Ix because it is half the moment of inertia of the circle. We know the area of the figure, We know the distance between the axes, and we want to calculate the moment of inertia with respect to the central axis. So we must rearrange the formula and simply substitute now the moment of inertia concerning any axis, which is half of the moment of inertia concerning the circle, meaning half of pi r to the 4th over 4, thus pi r to the 4th over 8. We can already substitute the rest into the formula. Here is the moment of inertia concerning any axis. Here we have the area of the semicircle and the distance between the axes squared. And from this calculation, we obtain 0.1098 PIR to the 4th. Next, we will move to the next slide and calculate the moment of inertia. First, we will calculate the centroid of such a T-beam, and then the moment of inertia with respect to this centroid. To calculate the centroid, we primarily have one axis of symmetry. If the figure has an axis of symmetry, the central axis surely passes through the symmetry axis of this figure. So we know where the vertical central axis of this figure is, but we do not know where to shift the horizontal axis or where the centroid of this figure is located. So we want to calculate the centroid of such a T-beam. So we need to divide it into simple shapes, namely two rectangles. In this way, we can designate one as the first and the other as the second. Now, having the division into simple shapes, we can draw the centers of gravity of these simple shapes because we know where they are. And now, to calculate the z-coordinate of the center of gravity, I will show you what I find to be the easiest method. First, we list the z-coordinates of the centers of gravity of each shape. So the z-coordinate of the center of gravity of this rectangle, designated as the first, is the distance from the y-axis of the first shape to an arbitrary y-axis. Here, we have marked that 7a is the height of the entire T-section. A is the height of the flange, the width of the flange is 4a, and the width of the web is a. So the height of the entire first shape is 6a, so this distance will be in the middle, which is 3a. The z-coordinate of the second shape is the total 6a, and also half of this height, which is 6.5a. Now we need the areas of the shapes, the area of the first shape and the area of the second, so that is not a problem. Now, using the basic formula for the center of gravity and the z-coordinate of the center of gravity, which means the z-coordinate of the first shape times the area of the first shape plus the z-coordinate of the second times, the area of the second shape divided by the sum of the areas of the first and second shapes. In this formula, the plus here indicates that we do it as the sum of two rectangles. You will see in the next video that we can also do it as a difference. If we are doing it as a difference in the case of, for example, some cutout, then there will be a minus in this formula. Now, substituting, we arrive at the z-coordinate of the center of gravity being 4.4a. So we measure, here we have the origin of the coordinate system as we have established, so now 4.4 comma, and at this point we shift the y-axis, making it the central y-axis because it is located at the center of gravity. Now that we have determined the center of gravity, we can calculate the moment of inertia using Steiner's theorem. We use Steiner's theorem when the center of gravity of the shape, or specifically the axis for which we calculate the moment of inertia, is distant from the central axis. So here, the y-axis of the first shape is distant from the central y-axis, and the y-axis of the second shape is distant from the central y-axis. In both cases, we will use the transference of Steiner's theorem. And if we wanted to calculate the moment with respect to the z-axis, note that the z-axis of the first shape lies on the z-axis of the whole, the central z-axis. And the z-axis of the second shape also lies, so it is not distant from the central z-axis. So here, when calculating the moment of inertia with respect to the z-axis, we wouldn't need to use Steiner's theorem. But in bending, we will be interested in the horizontal axis during simple bending. In general, And here also knowing that 4.4a is from the center of gravity to the extreme fibers, because we will be interested in the lower ones. We can also easily calculate that 2.6 will be to the upper extreme fibers from simple math. Now for the moment of inertia. We calculate it this way using Steiner's theorem. It is the moment of inertia with respect to the central axis, and now for each figure. It would be made in a general formula, which is the moment of inertia with respect to the horizontal axis, that is y for figure I, that is here the first, second, third, plus the area of this figure I times, and now this distance raised to the square, which we can always express this way. This will be the coordinate of figure I minus the coordinate z underscore c, which is this z underscore c we calculated here, plus or minus. That is, we either add this moment of inertia or subtract it. We add when we do the sum of figures. We subtract as if we were doing a difference. That is sum cutout. And the same. The moment of inertia of the next figure, plus the area of this figure, and the distance, that is, z, let's say here it would be 2 minus z underscore c squared. In our case, it looks like this. It will be the moment of inertia with respect to the first figure. Because we know this moment of inertia, it is a basic formula. Plus the area of this figure, here we already have written down, and z1 minus z underscore c squared, plus the moment of inertia of the second figure, the area, and z2 minus z underscore c squared. Substituting the numbers, it looks like this. The basic formula for the moment of inertia of a rectangle is bi times h cubed divided by 12, provided that if we calculate with respect to the horizontal axis, the dimension not taken to the third power is the horizontal dimension, so our b is the dimension parallel to the axis for which we calculate the moment of inertia. That is, if we were calculating with respect to the z-axis, the dimension not taken to the third power would be the parallel dimension, which would then be the length 6a. But here for the first figure we have a times 6 a cubed divided by 12, plus the area of the figure, and here I will not repeat anymore. Everything is substituted into this formula, follow it yourself. And as a result, we have 47.73a to the fourth, which means we have calculated the moment of inertia with respect to the central axis. We determined the center of gravity of the figure and calculated the moment of inertia with respect to the horizontal central axis for this T-section. And this will be an important skill in simple bending to calculate the moment of inertia for such uncomplicated figures. And that's it. I invite you to the next video, where we will already deal with the dimensioning of bending beams. Bye.